Okay, we're recording now, so I guess I can officially start. I have a bunch of things, miscellaneous things to go over, but a lot of it has to do with grading and scores. So I figured I'd start with that part. And maybe what I'll do is I'll start by working backwards. And this is available on the website right now, right in the What's New area. You can click to get this pulled up. So this tells you, this projects way into the week after next. Generally I go through this on the last day, but I decided I had all the data in my hands, I might just as well put it together. There's only a couple of things missing. The final is missing, obviously, and that's a big one. We're missing project number 2, so I took the liberty of giving everybody 100% just as an approximate, crude approximation. And I also have the very last quiz score missing, which will come in on Thursday. So this is what the numbers look like. And this is one of the powerful things about averaging, is it tends to, in distributions, exams may be spread out, quizzes may be skewed, but when you average more things together, things tend to bunch up more. I know that because I've been doing this a long time. It just happens that way. So I figured I'd show you this because this looks not all that bad. But when I get down to showing you the histogram for the exam and I get down to showing you some other things, you're going to say it doesn't look good. But this is kind of like, but this has got some optimism in it, I admit. But another thing that's going to happen on the final grade is that I will optimize. I will do a maximization. Right now the final is worth 30%, and the project average is it 20%?
Yeah.
10?
20 total between the two.
Yeah, 20 total. So I have an optimization where I'll bump that up by 5% and take the final down by 5% if whichever one gives you the better average. Okay?
On a per person basis? Or?
Per person basis. But right now, because there's no final in here, it optimized towards the project being the heavier part of the average. And then I just normalized by dividing through by a constant, namely 0.75, because that 25% was missing. Okay, so that's that. This is where the quiz average stands right now, less the last quiz. And one of those scores is down at 41. That's the lowest one. The highest average is 96.5, and this is with dropping the lowest quiz. Now, the last time I did an update on this, it was at 70, so it's shifted up by about 5. So it's got to looking better. This is some of the raw information, and I'm not really going to go through this. There's your project, and I've got your exam paper here too. We haven't started into the exam yet. So this is just up there, so you know it's there. Any questions on this part? I think the most significant thing on this document, at least, and this is on the website as a document together, is this preliminary right here. So I'm ready to move on to looking at the exam, which has its own histogram. And it's also on the website too. So I go to E2 solved, and at the bottom of this is where the histogram appears for the exam. So we had a high score of 98, a low score of 59, a mean of 76. So even though some of you, I'm sure, aren't happy, this is a better distribution than we had on the first exam. It's more, it doesn't have a distinctive nature of having two bundles of scores like I had before. If you guys want to come up and get your papers and projects. That's your project. That's your paper. Your exam is right there. So what I'd like to do now is just look at some of the problems and discuss what some of the problems with the problems were. So this first problem was a satellite transponder, and it was inspired by what I was working on the past couple of weeks at Emergent, actually, for the Air Force. Not an exact scenario, just sort of an impression that it left me with. So I didn't write out solutions to the two options, but as many of you know that there were two solutions, and some of you gave me both answers. I didn't require you to give me both answers. I was just looking for some sort of a sketch that basically would show the relationship between where you place the local oscillator, which in this case I chose the high side tuning. So my LO was sitting 70 megahertz above the input signal, and then the image is another 70 megahertz above that. So it's at 2.34. I honestly am confused that on several papers there was an extra digit that showed up, and I don't understand how that showed up. Some people had 2.346 or something. I don't know. I don't understand where that came from. More than one person.
It might have
But you have gigahertz here, and then you have 3 digits for megahertz, right? And we were talking about 70, and we had round, and we had megahertz or gigahertz 2.2. So I don't understand why what I thought I saw was a 6. Maybe it wasn't. I thought I saw a digit of 6 showing up on a couple papers. Maybe I took a 0 for a 6. I don't know. At any rate, 2.27 is 70 above 2.2, and 2.34 is 14 above 2.2, so that's the image. Local oscillator could be either above or below as well. I chose to think in terms of addition again, or subtraction, I mean. So I took 70 megahertz off of 2.8, what I wanted to end up at. So that would be the local oscillator to add to 70 to raise up to 2.8. About half of you chose to go the other way and said, let's pick the local oscillator to be 70 megahertz above, so 2.8. So the 70 megahertz from the IF comes in and subtracts, and that works as well. The bandwidths all the way around, I was kind of fairly generous on this. You needed to pick a bandwidth, but because this is a SATCOM system, or at least that's what I was thinking of, a transponder type system for satellites, my way of thinking was it's going to be working in fixed frequencies, so I'm not going to necessarily have a wide bandwidth. I'm going to keep everything narrow, and that's what most everybody did. So obviously the carrier had to match the uplink carrier frequency on the center of the bandpass filter to be practical, and then I just zoomed it right in on top of the signal, although it probably would be wider. I don't know by how much. It certainly can't be so wide as to let the image in, right? And definitely the IF filter over here has to be narrow because it's providing the selectivity to make sure no adjacent signals that would get down converted from the first converter would pass through that and leak through the system. And then the up converter, I again tightened the bandwidth on that down to 2 megahertz. But again, that could be made wider. You just don't want to let the image through of that either. Does anybody have any questions on those numbers? This made me think of something that's kind of interesting, that Linda Cash from RT Logic gave a talk at senior seminar about a year and a half ago about a program called SAT-ID, which most of you wouldn't know what SAT-ID is unless you work for RT Logic or work for the government. But bent pipe satellite systems like this, in other words, you have uplink and a downlink, those are resources that are sitting up there, and there's no stopping anybody from unauthorized user from using them. Does that make sense? It's a resource up there that you can shoot a signal at it, and it will send it back down, and it has a fairly wide beam antenna. So if you wanted to transpond something from one side of the country to the other, you could do it as an unauthorized user. And people have been known to do that. So there's a program called SatID that looks for unauthorized users and then geolocates them and then goes to take care of that problem, which usually is to just say, you know, please stop, but it could go further than that, is my understanding.
It's a very successful division.
Right? You know some about it. Yeah, okay. So you've heard of it before. It's actually, if you want to see her article, go to Lecture14a, my website there, and you'll see what she talked about at senior seminar a year and a half ago. Makes sense, though, doesn't it? If you paid for the satellite, are you going to let somebody else unauthorized use it? You can't put a door on it. I mean, you got to keep it available, so you just have a means of detecting things like that. Satellites are kind of an interesting technology piece because of the way the asset is so far away. Okay, number 2, this was not worth a whole lot of points. It was just because I wanted to see how good you could do at some analysis in a little way, what progress you could make. So the basic idea was to just expand out what's inside the radical. And when you do that, you get to see that you have sine squared plus cosine squared, and that is equal to 1. So that reduces down to this term. Then you get, there's a k squared term, and then there's a 2k cosine omega mt. And this binomial expansion formula says that you want to write that as 1 plus x. So I grouped the terms together as 1 plus something by factoring the k out. And the whole name of the game is, and we talked about this earlier but not in intimate details, k is made large compared to 1. So if I factor k out of there, I now have a term that's left over that's small. And you see that because I've got a k squared in the denominator and just a k in the numerator, so that's a 1 over k on the cosine term and then a 1 over k squared on the other term. So that is my x in the parentheses here. That's the x. And definitely for k much greater than 1, x is, magnitude is much less than 1. So that satisfies that.
So what happens, what about the 1 though? You're taking out a k squared there, but shouldn't the 1 be over k squared as well?
I took out k squared, so that leaves this 1, right? I brought out.
Oh, I see now. Okay.
Right?
I get it.
Is the algebra good?
Yeah.
All of you did amazingly different things. I mean, in grading this, it was like everything. I saw lots of different variations. So when I looked at this, I said, okay, this term right here is not just 1 over k, it's 1 over k squared. This is after I used the binomial approximation, which keeps the first 2 terms. So it keeps this constant, and then it comes up with x over 2. So I said that term essentially goes to 0. And then I brought the k back through again. So I had a 1 over 2k and then a cosine omega mt. So the term of interest is this, but we have to take that k along with it. And I don't know if you remember, I ran a Mathematica simulation. Remember when I changed, I had a slider, adjust the value of k, and the whole waveform went up and down on a pedestal of DC, but then the sinusoid got recovered out of that. Okay, next problem. This one I thought would be easier than what it was, and once you know it, more often than not, people got hung up on one thing that I didn't expect to be such a hassle. So you want to have the instantaneous phase, and the instantaneous phase is the entire argument. So it's the entire argument of the cosine. Remember, instantaneous phase is everything. Phase deviation is just the piece separate from the carrier, which is linear phase. So when I said instantaneous phase, you have to have this term, which is due to the linear phase of the carrier, just ramping in time. And then you have to get the phase deviation term, which means you have to plug in the m of t into the integral. And the big surpriser is that you have this u of lambda in there. So that u of lambda makes your lower limit go to 0. And I won't say countless people missed that, but a good number of people got confused on that and didn't have a lower limit, so then they didn't know what to do. So the lower limit of 0, plug in, and you're basically getting, a step response out of this thing. You're getting that m of t becomes a charge up then. So this term right here is basically sloping up like that. Plus the linear phase from the carrier. This one I think was, I don't know whether this was, I meant this to be fairly easy because it was only worth 5 points, and I think, Kevin, you wrote something on your paper that definitely stuck in my mind. You were disappointed it wasn't worth more points, right? Or not? Is that what your comment was? Okay, I interpreted it correctly then. I probably had this at 10, and then I'd rejuggled the points and I set it back to something else. But it's still, people still messed up on it because one of the fundamental things that seemingly got missed was that. And I think, Robert, you asked me about this, or somebody, okay, somebody asked me during the exam. That was like a piece of information that you had to solve for. Because you know that the sideband powers are the carrier amplitude AC times Jn of beta. So this was a given piece of information, so that allowed you to find out what AC is. So AC is what, 192.3. Or did I do that wrong? It's 92.3. Magnitude of 92.3.
No, it's 192.
It is 192? Okay, so I missed writing that down over here. So I get points off. So those are the numbers to fill in. Should have been worth more points, I agree, because there was a fair amount of work involved. Okay, FM modulator, pretty straightforward, 7.5. You just had to identify the numbers, and you had to make sure that you ignored that right there, which was kind of like running interference, so some people latched onto that. This is the amplitude you need, though. The amplitude of the message is the 15. So that goes in here, and then you divide by 10 and multiply by the deviation constant of 5. So you end up with 7.5. And then part B is just the continuation of the problem, saying, okay, what's the approximate bandwidth of the modulator output? And this really wasn't that necessary, but we remember that the 0.98 or 98% containment bandwidth for sinusoidal FM is equivalent to 2 times the quantity beta plus 1 times FM, Carson's rule for sinusoidal modulation. So it's 170 hertz. And then part C was, again, a problem that caused a little bit more confusion than it probably should have. You need to get the deviation ratio, D, which is delta F. In this case, the problem's been modified, so the maximum amplitude of the message is 2, and it's a generic message now that has just a bandwidth of 200 hertz, so you have 2 times the original deviation constant of 5 hertz per volt divided by 200, so you get 0.05 for the deviation ratio. And remember, Carson's rule for bandwidth in the general case is 2 times the quantity d plus 1 times w. So I look at that and I say d of 0.05 is much less than 1. So what qualifies to be much less than? What should qualify? 1 order of magnitude, 2 orders of magnitude? I generally say 1 order of magnitude is good enough to qualify. So it's less than an order of magnitude smaller. So it's narrowband FM. It's very close to the bandwidth of just 2 times the message that you're going to get out. Which for a few people, you wrote all that down and then you reasoned in the other direction, which I guess that was just carelessness. I don't know. Right? I don't remember who that was, but at least 2 people did that I can think of.
I just wrote down the wrong word at the end.
Okay.
I saw W, and so I knew it was narrowband, but I wrote right down.
Okay. If you were in the jury, or if you were testifying in the court, right, once it came out of your mouth, could you take it back again? I'm just teasing you, but... Okay, what's the purpose of preemphasis and de-emphasis? It's to reduce high-frequency noise in the demodulated output. It has to do with the fact that noise that enters an FM receiver, kind of like the interference, becomes stronger as you push to the edges of the message bandwidth, because you get that 1 over F, 1 over FM effect in the strength. So you pre-emphasize at the transmitter, and then you can de-emphasize to keep the message signal flat in frequency, but bring the noise level down. And this last one was a really hard one for me to grade because I just wanted words, and I kind of didn't see very many people write down what I was looking for. I just wanted you to say proportional to the input frequency deviation, which, a lot of people just said, oh, it's the output of the ideal frequency discriminator. I realize it is true. It's just d phi dt. That's true. Because that's, the derivative of the phase deviation is the frequency deviation. I was thinking in terms of words, though, because this was a fill in the blank, and generally blanks are words. You can take exception to that, I realize. How do I feel about words these days? It's because I had an editor beating on me for so many months. I tried to answer and make statements with math and equations, and repeatedly I was beat up. You have to explain this in words. And my brain kept saying, but the math tells the answer. But, engineers think that way. I guess we like to use math as the answer, but people that read books, I don't know. The editors wanted words, so became more sensitive to that. Okay, phase lock loop. Have some constants in here, multiply the constants out to get kT. And what seemed to be the problem, the biggest problem, was keeping the 2 pi in there. And I tried to make it kind of blatantly obvious that the 2 pi was there by putting it right over here, so that was in radians per second per volt. And then the dimensions of everything else collapsed down. Now, one of the things that maybe bothered anybody, I was nervous about when I first wrote up the solution, was the units there of volts per radian. But nobody seemed to be affected by that. Does anybody want to know more of the story on that?
I was curious about why
Pardon me?
I was curious why the units didn't necessarily work out to a radians per second.
Well, this is a case, and I have a phase lock loop book that I teach out of that has this in the very first chapter and kind of poses this as a dilemma. And I thought of it after the exam, that I probably would have been better served by just simply not showing units there. Then you would have, but nobody seemed to sweat it out because I didn't see any signs of that on the paper, unless it was going on in somebody's head and they didn't talk about it on their page.
It did. went through my head. I just crossed out units and it didn't work out, so I knew what units should be.
Okay.
As we said.
Well, those of you that took the comm lab, though, had to wrestle with it because you characterized a phase detector and you put voltage in and then you got voltage out in response to a phase error. And that's where the units come from. But they sort of disappear on you because you're not really putting in. These two values are embedded inside of the signal. They're inside the arguments, right? There's a cosine of omega ct plus theta, or phi, I guess. And then coming up from underneath that is sine omega ct plus theta of t. Then there's a multiplier if we're using a multiplier type phase detector. So the difference, or the signal that we're interested that comes out of here, ends up being the sine of phi of t minus theta of t, but actually there's another term on here, and it's called kd. So that kd comes about from the amplitudes of those input signals, like there would be an AC and an AV for amplitude of the VCO.
And a 1/2.
Yeah, and then a 1/2 comes from the trig identity. So that's where the 1/2 would come from in an ideal setting. But then this thing right here, what's that doing? That's taking phase difference and it's going through the sine function. So what happens to the units when you come out of the sine operator? They disappear. So you just have voltage now. So that's where the confusion comes in. Actually, what the slope business is, though, if you look at the output of the phase detector versus phase error, which is phi minus theta, and you get the slope right at this point, that slope actually is going to be kd right at that point. And it actually is so many volts per radian. But then, like I said, the units disappear when you're putting in phase, so those units go away, and what sets the units as all the way around on the loop gain is not that constant anymore, because it's being driven by a radian difference. So what drives the whole thing is the radians per second there, and then the per volt effectively is getting canceled by the volts over there. I don't think I did a perfect job of explaining it. It's still a little bit mysterious, but it does work. And if you designed a loop in the lab, if you were taking the lab and you designed a loop and the lock range matched your calculations, which it did, right? Is that true? Yeah. It has to work. Pardon me?
Just a little bit off.
But I mean, within the error of measurement or something. But it does work, so I should have just left the units off. That was an afterthought, so I screwed up. I should have just left them off. At any rate, the total lock range is controlled by that 1/2 times 20 and then times the 10 to the 5th, so that becomes 10 to the 6th in hertz. But in radians per second, it's 2 pi times that 10 to the 6th. But then you have to take that off because I was asking for the lock range in hertz. So you had to divide by 2 pi. And the lock range, the total lock range, is plus and minus kt in radians per second. So it's 2 times kt is the total range, and then divide that by 2 pi, so you get 2 megahertz out of that. Closed loop transfer function was just filling in the blank from what you knew from class, kt over s plus kt, and then kt in the closed loop transfer function has to be in radians per second. And the way you can justify that is saying s has got units on the frequency axis of radians per second, so that has to balance the units there, right, in the denominator. And the units on top is radians per second, so the units cancel as it should. Okay, the closed loop transfer function up to the VCO input from the input to the phase lock loop is this one, and this was, everybody did that S over KV. Then you just had to plug in the numbers, and basically you're getting this sort of a term out of there, the S over S plus 2 pi, or plus KT. And that's the transfer function, but because if you use the phase lock loop to modulate FM, when the signal comes in, phi of t is written in terms of frequency deviation, has got an extra s in the denominator because you've integrated frequency deviation to get phase deviation, and that puts a 1 over s in there. And that's why in the analysis we were doing earlier, you have something like that, and then you have little kd. That cancels, and then that's what makes the output look like the input with a low-pass filtering action on it. And that's what I just wrote this down here just as a reminder. The last part is the final value theorem, which is the way I approached it from the linear phase lock loop model. Now, some of you just said, because you probably had this on your cheat sheet or something, you had the static phase error for a first order loop in terms of a frequency offset was the arc sine. So some of you got this answer from the arc sine, and it agreed because the error is rather small. For the first order phase lock loop, you have to have what's called a static phase error to counterbalance a frequency offset at the input. And that's what this final value theorem approach also shows you. It's going to be delta of omega over KT. In this linear loop model, the actual model involves the arc sine, which a few of you used. Congratulations if you did that, because that was probably the more appropriate way, but I wanted you to be able to see it in general terms too from the final value theorem, because that inverse sine is only good for the first order loop. That doesn't hold for other types of loops. Whereas the final value theorem would work for any type of loop. Okay, this one is the one I changed during the exam. So I made it be 2.5. It's magic. I don't know why it does that. I pull the pen away and it disappears. Doesn't like it. Doesn't like me right now. I don't know what's going on. I'm not going to fight it anymore, though. At any rate, the pass band is at 2.5, so there's 1.25 kilohertz out to the edges. Hey, it is disappearing all the time now. So that captures the carrier plus a sideband above and a sideband below. So the analysis model would be that. And then you just plug in. Now what I saw as a fairly common error, I guess, was not getting beta equaling 2. It's pretty interesting the way this works now. And that's because that had a 2 pi inside of it, right? So that meant that FM was 1,000. So 1,000 divided into 2,000 gave you 2. So it was a somewhat common error to have beta equaling 1, because you just looked at 2,000 over 2,000, not thinking of the 2 pi, and got the wrong beta, and then that led to the wrong answer. Okay, the last problem was a synthesizer, and maybe I made this problem too convoluted because there's only a few people that got 55. It sort of started off being just a simple synthesizer, and then I said, how can I make it seem more realistic, like getting the local oscillator for a receiver? So I threw in there the idea that I wanted to receive a signal at 99.3 megahertz. I wanted to use high side tuning, and I wanted the IF at 10.7. The timing is now perfect. The delay time from when I lift the pen to when it erases. It's very consistent. So you figure out what FLO needs to be for high side. It's going to be 110 megahertz, which is a pretty nice round number. And then you analyze what the synthesizer is doing. And I just wrote down the equation straight away, but that was the way I approached it. I said FLO is going to be, first of all, 2 times Fs, and Fs is going to be what? It's going to be Fref over 100, because that's the compare frequency in here, which is 0.1. This is really confusing. 0.1 megahertz. Another mystery to solve. 0.1 megahertz or 100 kilohertz is what Fref, or what the reference is right in here. So that's the compare frequency. So that's Fref over 100. And then we know that the action of matching that requires us to set this divider to Fs over 10 times n, because that's the effective divide ratio. So effectively then Fs has to be n times 10 of that Fref over 100. So I plug all that together, and then I solve for n, and I get 55. I don't know what else to say about that, except I'm amused about why my pen doesn't work right now. Any questions? Maybe it'll work on one of these other documents. It's been an interesting day. Yesterday I went to come to campus and the spring broke on my garage door, so my car was trapped on the inside because I have a heavy door. I couldn't raise it. And that just got fixed about 2 hours ago. The week before that, the hot water heater broke at our house, so that had to be replaced. So there's just been a bunch of little things. And so this is like another thing to add to the collection of things that keep happening. Robert?
Just like one thing before we move on from the test, you said that at the end of the semester you're going to maximize or optimize your grades. I know it's kind of hard to know what you'll be doing if you're just going to have all the data, all the grades.
No, I explained that earlier. I said that I would maximize with respect to the projects and the final. So that's what I meant by maximizing, optimizing.
Maximize the grades of the whole class or each individual?
Each individual. So when I take your entry on the spreadsheet, I will have 2 formulas. I will do one calculation based on the final being 30% and 20% for the project average. Okay? And then I will say I will compare that against the calculation of the final average based on 25% for the project average and 25% for the final. So I'll do this kind of a thing. I'll do one calculation like that, and I'll do another one like that. And I'll choose whichever one gives you the best number. And I'll do that for everybody independently. And then all the numbers are averaged together, though. It's not like I can set a template and say, these are the thresholds, and now I'm going to optimize and which side you land on. It's just, it changes the class, instantaneously. So it's the only right way to do it, in my opinion.
So the quizzes and the exams are going to have, combined are going to be worth 50% either way. And they're
Yeah.
aren't going to change at all. It's just, okay.
Yeah. So it's 20, 30, or 25, 25 for the things that I'm optimizing over. And right now I'm throwing out 1 quiz. I could be more generous and throw out 2, and I guess I'll leave. That'll be up to my discretion, right? If I feel like I want to show more mercy in that regard, and the mercy there would mostly be for, the low quiz averages, honestly speaking, are mostly due to people just not being here to take a quiz. So if you missed 2 quizzes right now, you're missing 1 whole quiz grade then. And there are some people that are like that. So that's why we have some low averages on the quizzes, because it's not because they did necessarily really bad on a quiz grade. They just simply didn't, they got a 0 on because they weren't here. Okay, moving on back into Chapter 3. Let me just give a quick preview. I've decided after reviewing the notes earlier today, I'm going to jump into Chapter or Appendix A right after we get done with Chapter 3 today, and then put off this introduction to digital data transmission into next week to see exactly where I stand. It might be that I'll talk about it only on Thursday, and it will only be just for information purposes. Whereas I've put up an assignment sheet for Appendix A, and it's called homework sheet number 8. And I thought I had it up here. I don't see it up. I thought I already had brought it up, but it's on the website right now.
Are you going to talk about the project in class?
I want to wrap up Chapter 3 because we're so close to being done with it. And in finishing up Chapter 3, what I'm going to do is I'm going to look at this old exam from last year that had a couple of problems on it, namely with frequency division multiplexing and time division multiplexing. So I'm going to use the problems from this old exam too, just to add some additional discussion into that topic from Chapter 3. And then that's also, in effect, my plans for the quiz on this Thursday. So the quiz will be motivated by these two examples I'm going to go through. You won't have a quiz over Appendix A, but to show you how crazy I am about Appendix A material, I was looking in my old notes. I have a practice quiz, number 9, for Appendix A, but I've got 4 versions of it. I've got 9, 9A, 9B, and 9C, or effectively got 4 different. So you're going to get all that stuff for extra practice problems thrown out next week to work off of. I haven't posted them yet. Yeah, but it will emphasize. Appendix A will get a little bit more emphasis. And it's a bit of a letdown. Appendix A is not very hard, so you won't be disappointed. Yeah, I'm saying that facetiously. There's no calculus involved in Appendix A for sure. So what I want to do is go back to where we were. We were talking about multiplexing. We already went through this, but just to review through, there are 2 types of multiplexing that we're talking about, and you have to have some understanding of. Frequency division multiplexing is where you put messages on subcarriers at the transmitter, and you put them up on different subcarriers so they're all disjoint. By disjoint, I mean their spectra don't overlap. Then they enter a common modulator and get sent off through the electromagnetic spectrum as free space propagation. It could be on a cable. I mean, think about what is a big multiplex scheme that you can think of that's probably in just about everybody's life when they're not doing homework. Computers. Well, what else though? Yeah, cable TV. Cable TV is just one big. Well, I'm just saying that though. You sometimes watch TV, right? It's one big multiplexed environment where all those signals are multiplexed together. I mean, you'd say they occur naturally. They occur naturally when they leave the antennas up there, but the cable TV system purposefully, multiplexes them all onto the cable. Not with a common carrier, though. They're just located on the carrier. But it's in a sense like multiplexing. There's not a modulator and demodulator. Formally, multiplexing in the normal sense has all of this associated with it. And it doesn't have to be an RF modulator either. It could be what Jason's project is, senior design project. You're putting it on fiber optic, right? So you have a fiber optic means to fiber systems can bundle up a whole bunch of signals and then put that into one laser diode to send it over a long piece of fiber. But we're talking about RF modulators here. So at the receive end, you just have to first take the composite signal off the carrier, FM or AM, or intensity modulation is what they usually use in light wave systems. And then you have to have the individual subcarrier demodulators. And generally, to keep interference down, you generally put, oops, okay, it's not going away. Generally put some bandpass filters in front just to keep things clean into those individual demodulators.
Is that so you don't get image frequencies, that way you don't demodulate the subcarriers first? Or
Images are just general interference. If it's kind of weird, I have freedom to draw again. It's kind of like quite the luxury. Suppose these were all the subcarrier signals that were up there. So there were 4 different subcarriers. If there's a sensitive front end for demodulator number 1, and you were wanting to, oops, wrong hotkey. Suppose this is the guy that you were looking for. You wanted to get that one. Why expose demodulator number 1, let's say, to those other 2 subcarrier signals? They could possibly just hit that front end amplifier and overload it. If it's a broadband front end, it's going to have to deal with 3 signals all superimposing, all, at different frequencies, all right, but you don't want to stress it out by having it amplify or process signals, multiple signals. Does that make sense?
okay.
I don't know if you ever did any experiments in electronics, but you could, if you had an amplifier and it was amplifying a signal that you could hear with your ears, but suppose your amplifier could also amplify signals that you can't hear, and you put both of those into your amplifier and you cranked up the one that you can't hear, is it going to have any impact on the signal you can hear? Think about it. A real physical amplifier, what happens when you drive it too hard? It starts clipping. So if that signal that you can't hear is also with the signal you can hear, it'll force it into saturation, and you'll be disappointed that this signal you didn't care about is actually causing you harm. So the filter can protect you in that regard. And guard bands are talked about, so you might have some separation. PSTN was a good example of this that was used a long time ago. A practical example that's used today, I guess I should open this up, is FM stereo. And I went through this fairly fast, but this puts a composite signal on at baseband, which is perfectly okay. So it's on no carrier frequency. That's the left plus right. So that's coming in here. Baseband because it's centered on 0. And then there's a signal that's put on a 38 kilohertz carrier, and then there's a tone at 19 kilohertz. So those 3 signals go up into the FM modulator. They get scrambled up effectively in the FM modulation process, so you can't discern any one of those 3 signals if you just intercepted the carrier without a demodulator. It's like a composite signal. But then when you come back into the discriminator, now you can separate them out and work with them. So the FM discriminator, FM demodulator gets back the 3 composite signals. And then I'm showing filters again to effectively act like strainers, or some physical means. It's like straining out the signal of interest in this collection of 3 disjoint spectral signals. So you get back left plus right. Left minus right takes an extra processing stage because you have to do a coherent demodulation on it. And to do the coherent demodulation, you obtain that coherent carrier by frequency doubling the 19 kilohertz pilot that you also get off of the signal. So that's one of the things that you can do with a multiplex system, is you can put a pilot signal in there to help aid the demodulation. Normally we thought, when we talked about coherent demodulation, one of the things about that was we had to recover that without any assistance. but pilot is an option. And with a subcarrier system, if you have a lot of other signals multiplexed together, reserving some bandwidth for a pilot that's harmonically related to the carrier is not that big of an impact on spectral efficiency. It does take bandwidth to put that pilot in, but it's not a tremendous amount of bandwidth. So before we move on, hopefully my voice doesn't go well, go look in exam 2 from last year and just see, sort of in preparation for the quiz on Thursday, here's another example, another take on that. And you probably have this in your notes because you probably printed this or put this on your computer when you were studying for the exam. So this is another variation on FDM. I just said, suppose you have a double sideband carrier at 10 kilohertz, one at 20 kilohertz, and then I threw a pilot in at 40 kilohertz. I FM modulated it onto a carrier at 1 gigahertz. I didn't really care to specify the deviation constants or anything. I was just interested in having you draw the block diagram from the FM demodulator onwards. So you just FM demodulate at 1 gigahertz. You know you're going to get back that composite FDM signal. Put your bandpass filters in to get the signals of interest back in the different subcarriers. And then the 40 kilohertz pilot is for demodulating coherently the 10 kilohertz and the 20 kilohertz signals. So I rigged up a system that I just said, let's put a bandpass filter at 40 kilohertz. Ideally, this probably would be a phase lock loop that would be locked on to 40 kilohertz, and then I could divide the output of the phase lock loop by 2 to get 20, and by 2 again to get 10. And then I could feed that into some mixers to get coherently demodulate the two information-bearing subcarriers at 10K and 20K.
So typically is your pilot carrier multiple or even multiple with the subcarriers?
Yeah, it has to be harmonically related in some convenient means.
Okay, because there are parts that can divide by 2, multiply.
Right, yeah, because you could design a synthesizer that could lock onto the reference that's coming in as one of the subcarrier signals, and then regenerate a coherent signal.
So then is a pilot basically, the purpose of a pilot is you want it as kind of like your local oscillator for when you're coming back down, right?
Yeah, for not a local oscillator in the microwave or megahertz range, but
Right.
As a reference for demodulating something that you coherently modulated. You want to coherently demodulate it. And that saves efficiency because you wouldn't typically put an AM subcarrier in here and then waste a lot of power, because remember, AM wastes a lot of power just to put up a carrier and then use envelope detection. You might do that though. I'm trying to think. See, the AFSCN waveform that I've been telling you that I've been working with, it's got a bunch of subcarriers that they use for different things in this satellite telemetry and command and control operations. I'm pretty sure they don't use any pilots though with that. I think they derive the clocks from the data bearing waveforms themselves, so they can have things on at DC, at baseband, and then they can also have other digital modulation placed on subcarriers, and they derive the clocks natively from that. They don't use a pilot. I'm using a pilot here though because I'm trying to make it simple so you can understand it, and that's kind of helps you get in the mode of understanding how frequency division multiplexing can be useful.
Is there any benefit to having a pilot off by itself and not making it just one of the signals AM and then divide just that one AM thing down? But then you wouldn't have to divide. You wouldn't have to at least save a divider and save.
Okay, so let me see if I get a take on what you're saying. You're saying get rid of that, maybe put
AM there.
make that one AM, so we have a carrier. In the business of the AFSCN, that's called a residual carrier if it is included. It's like we have a residual carrier. It doesn't have to be a fully AM signal. It just has to be some amount of carrier that you could lock onto it. So yeah, that could work too. And then to build off what Robert's saying, he's saying that you would build you wouldn't necessarily envelope detect subcarrier number 2, but you would attempt to basically set up a phase lock loop in the demodulator that would basically set a very narrow passband around 20 kilohertz and lock onto that component and use it for demodulating that subcarrier, and then divide it by 2 to use it to demodulate the 10 kilohertz one.
Because it'll lock onto the most powerful.
The phase lock loop, it likes to lock on to strong harmonic components. It doesn't like to lock on to modulation, which is all kind of fluttering around. It's looking for a steady sinusoidal type signal. So, but it'll work better though. It'll have less jitter on it, the phase lock loop output, if it doesn't have to contend with data modulation sitting around that 20 kilohertz. So by having it isolated off over there at 40 makes it more robust. But it costs more because it takes up a little bit of bandwidth.
Would it be just as easy to put the carrier at the 10 instead of the 20 as well? Would it make a difference?
Right.
Other than the fact that we just go up as high or something.
The picture heights were kind of relative, but
One other question was, if you bring it back to baseband, aren't both those going to be overlapped on top of each other?
There's 2 different outputs.
yeah, but that's you have 2 different demodulators on each of the subcarriers. So this path is get you signal 1, and this gets you signal 2. It's beautiful, right?
Yeah.
It's old too. It's been around for a long time, but it works. I mean, and this is the thing about communications theory. Just like any branch of engineering, not everything is new and has changed every second for the last 10 minutes, let's say. We get tired of that. I mean, I think you're going to get tired of that too. You're going to wish throughout your career that some things could just stand still a little bit so you could really get to understand it. When technology changes so rapidly, it'll be one of the challenges you'll face. Things keep changing, but this is still around. It is not as popular as digital multiplexing schemes are, for sure, but it's tried and true, and it has good, easy to understand properties. As a matter of fact, I contend that this is like the most obvious of the schemes, and I think when people were dreaming up ways of putting more information on a carrier so they could package it up and take it off again, this didn't require a lot of super intelligence to do that. However, it doesn't mean that it's not free of issues, though. Your demodulator, for example, could have some harmonic distortion in the linearity of the discriminator that could throw up clouds of clutter. I mean, this thing could come through just fine, but then it could be that there's some remnant that shows up over in here, some second harmonic distortion from the demodulator that throws up some clutter over there. When I say clutter, I mean just some residual signal that will cause interference, and then you have to be careful with linearities and things in the processing. So that's a good segue into the next topic. The next type of modulation or multiplexing is the time division scheme. And that was the next one that was talked about. Well, quadrature multiplexing was talked about, and I can say more about that when we get in to take a look at Chapter 4. This one is definitely useful too, where you use the in-phase and quadrature to separate signals. This one is not as old, though. It's still very useful. This requires a coherent carrier, though, for sure. So you can't really make this work without having a coherent carrier, because otherwise the signals are just scrambled together. And so you're likely to get crosstalk if there is error. So time division multiplexing, though, is the other main type of multiplexing. You can apply it to analog sampled signals, which is pretty old-fashioned. Remember the jet airliner sound tube headphone thing I was talking about, that's how they did it a long time ago. They time division multiplexed analog signals. And that's what the book talks about. So the book actually looks at it this way. They called it analog time division multiplexing. And think of commutators that are synchronized, that have to be synchronized too. And then you just take a sample from source 1 and make sure the commutator at the other end of the channel sends that sample out into here, and so on and so forth. So what about synchronization? How do you think that works in this scheme? I personally think in the jet airliner scenario they had an extra wire that sent a synchronizing clock to each seat along with the little analog demultiplexer or decommutator thing. In digital version of this, though, you have something called frame sync that's included into the bit stream. Something that, a unique word that you're looking for that helps you get synced up with the data frames. The interesting thing when you go through the analysis here for the TDM versus the FDM, and that's what's talked about in here. How many samples do you have to send? You have to have a sampling rate at twice the bandwidth of the signal. And then if you put up how many samples you need per t seconds, it's the sum of 2 times all the individual bandwidths to get all of that to play together. So that the total bandwidth ends up just being effectively the sum of the individual bandwidths. And if you did FDM multiplexing with single sideband subcarriers, then you get that same bandwidth efficiency, because remember, with single sideband it just takes the message bandwidth, and if you pack them all right next to each other, that would be the overall bandwidth. So there's a certain niceness about that. That's in the limit, though. In FDM, you need guard bands, as you learned about when you did project number 1. And in TDM, you might need guard bands if it's analog TDM. Digital TDM, not really.
Quick question. Could you do single sideband for FM modulation as well, or does that not make any sense?
No, it doesn't. I mean, to me it doesn't make any sense. I don't know how to do that, actually, because the FM modulator is nonlinear, whereas single sideband and the Hilbert transform, that was all linear signal processing. So it's that business of, you know, putting in an input to a VCO and making it instantaneously change frequency. That's a nonlinear relationship in terms of the way it produces the output spectrally.
Well, I guess the reason I thought about that is because your spectrum is still symmetrical about.
Yeah, that's true. But you can't control it in that sense, with the modulator at least. As soon as it goes in the FM modulator, it comes out. Yeah. You could have a combination of frequency division multiplexing, though, where your final stage of modulation was single sideband. And that would be a strange setup, but you could put in a bunch of FM type subcarriers and then have a single sideband final modulation. Gives me an idea for your quiz, which if I take that pathway, you can blame Robert's idea, but I don't know. Just, you're making me think, though, how I could have you look at that. Okay, TDM. I don't think that's done, though. I can't think of a system where that's done. The AFSCN program uses phase modulation. They always use phase modulation, but they have FSK, they have direct modulation of phase shift keying, and I guess those are the main types of modulations that they have on the subcarriers. So pure digital multiplexing is just like the analog multiplexing, except we're just combining bits into one bit stream. So a good example of that is the PCM and CD audio, where you've got left and right audio. So you've got 44.1 kilosamples per second. You've got 16-bit quantizers, so you've got 16 bits per sample. And then you want to multiplex left and right. So that's how you build that up. You've got 2 bit streams at 44.1 times 16 bits per second. So the total serial bit rate is 1.4112 of just raw data. That's without any framing or overhead, framing/overhead added into the stream. This is kind of what project number 2 involves, because it's PCM and you don't have to worry about framing, but you could experiment with it. Just all you got to do is get off by a couple of bits when you get to your depacking this, unpacking the serial bits, and then send that into your PCM decoder and listen to it, and it's total nonsense. Senior design projects that have had to deal with this have generally not thought about synchronization right away, and when they get to this problem, it's like, oh, how do I do that? And if you're looking at standards, though, the standards have some means of synchronizing. Digital telephone system is a good example of this, though. It's called the North American Digital TDM Hierarchy, and it's based on the fundamental smallest quantity inside this hierarchy is one voice channel. And one voice channel is taken to represent 8,000 samples per second. Think about that. You have to sample at greater than twice the highest frequency, so that means we have an audio bandwidth of 4 kilohertz for human voice. Sample it at twice, get 8,000, and then they use 7 bits of quantizing, and I don't know the full details, but they have one extra bit they use for signaling on the line. So 64 kilobits per second per voice channel. So then you have these different orderings in the hierarchy. A long time ago, before we had cable modems and things like that, and the only thing you had was a dial-up, people would talk about getting a T1 line into their office. So a T1 line is the 1.544 megabits per second, and that corresponds to 24 voice channels at 64 kilobits per second.
So that's like how many different lines?
How many analog voice channels would be multiplexed digitally into that T1 line? Right now on the campus we have, I don't know whether it's T5 or something, but it's fiber something, and it's one of these higher rate lines, but I believe it corresponds to something in this hierarchy, and this hierarchy goes up higher and higher. But this is established a long time ago as well. Does anybody know anything about this from where they work, maybe? Sometimes interns maybe deal with the interfaces that are out there and what the rates are that come in. I mean, cable modems don't correspond to T rates, but like I was saying, T1 used to be a pretty nice thing to have, but T1 is actually pretty low right now, right? Most cable modems get you in excess of 5 megabits per second that you get to use all by yourself. So I'm going to look at an example of that here in a second, but the last thing that's in this chapter is a little section called General Performance of Modulation Systems in Noise. So this is looking way ahead into another chapter, is what this kind of refers to, and it's sort of thinking in terms of analog modulation, where you receive the signal that you transmit with additive noise present. And this is what Appendix A is going to talk about. Where does this additive noise come from and how do we model it? So in the book's notation, a received signal would come in with some signal to noise ratio after some pre-detection filter. So you'd have a signal to noise ratio at the pre-detection point, but after you have some bandpass filter to at least eliminate out-of-band noise. So the idea is the message occupies a certain bandwidth on the carrier, and then your receiver front end has a filter that sits over the top of it to make sure it passes the signal of interest but doesn't let all this noise through that sits on the other side of it. A typical scenario would be the signal is sitting in here, and due to front end noise that we'll be talking about in the next chapter, there's some noise and not. And by putting the filter over this, we're trying to let our signal through but not let extra noise come through. After the demodulation process, though, you go through some sort of demodulator. It might be FM demodulator, it might be a PCM system or something else, and then you've got what's called the detection signal to noise ratio. That's the power in the message divided by the power in the noise post-detection. So you have two different ratios, and generally systems are spec'd in terms of the pre-detection signal to noise ratio, and it's interesting to compare how different schemes post-detection SNR varies relative to the pre-detection SNR. So single sideband, double sideband, and quadrature multiplex double sideband, and coherent analog demodulation all operate in this linear relationship. When you get into FM with different deviation ratios, you get a boost in post-detection SNR, which is why FM sounds so much cleaner than AM, but all of them suffer from a threshold, and the threshold is basically when you get your pre-detection SNR down too low, like when you're driving to Denver and you're listening to a Colorado Springs station, as it starts to fade, it all of a sudden it's just gone, and that's because you're hitting this knee right here and you're just dropping off very rapidly. Whereas when you listen to an AM radio station, it just gradually fades away ever so notably. Like if you were listening to a baseball game, let's say, driving a ways away, it would just get weaker and weaker, and then it's like, oh, I can barely hear this, but it wasn't an all of a sudden gone kind of effect. The PCM, which is what you do in project number 2, has a similar nonlinear characteristic, because what's going on is when you're above the threshold, essentially all the bits are getting through correctly. And when you get down to a certain knee point here, you start making bit errors in all of those bits, and that degrades your performance rather rapidly. And you're going to generate some curves that look kind of like those orange curves in project number 2. And then you're going to experiment with this idea of repeat coding and partial repeat coding. So you're going to repeat bits that make up each sample, and then you're going to do partial repeat coding and decoding on just the most significant bits. It's figuring that if you make errors on the least significant bit, that hardly impacts the sound quality, whereas the most significant bit gets errored, and that's a huge amplitude error. Have to talk more about that on Thursday. But just one quick look at another problem that appeared with the multiplexing. So I want the quiz to cover both types of multiplexing, so I'll give you a small problem on each. This is straight digital multiplexing, where we've got two 1 megabit per second streams coming in, and then we've got some analog signals that are going to get PCM encoded. So the analog signals each have a bandwidth of 100 kilohertz. We want to sample them at 12 bits per sample. And I've already said that we're going to use oversampling. We're going to set FS at 2.5 times W. So the multiplexer is just going to multiplex bits, but it's going to have to get the two analog sources from a PCM encoder at 12 bits per sample. So that takes the 100 kilohertz times 2.5, that was the sampling rate, then times 12, the number of bits per sample. So each of those sources is 3 megabits per second. Does that make sense? So now we have 2 1s and 2 3s, so that's a total of 8 megabits per second. But in a real system, there'd probably be some framing bits that have to get stuffed in there. So you've got all your payload, and then you've got some frame word.
Is that just to catch it, or have something to pick up.
Yeah, so you know how to get it back together, but you don't have to put a frame word every collection. You just put them interspersed every so often.
Just so it can relock on.
But that would have an overall effect on your total bit rate, right?
Yeah, it ups the bit rate and it lowers your efficiency slightly. But what choice do you have?
No, yeah, you don't.
So that's a whole study into itself, coming up with a unique word that won't be misunderstood. And it's always going to be misunderstood because the bits are random, so there's a chance that it will see that. But the frame sync word comes along often enough that when you're doing a correlation, that's correlation functions we talked about earlier, it will stand up tall enough that you'll be able to say, there it is, I need to call that the start of a new frame. And most packet communication systems use it too. They call it starter frame delimiter pattern. They look for in the start of a new packet. Bluetooth, I know, uses it. Anything that uses packet communications has to have a starter frame, so you know how to find it. Okay, we'll be looking at Appendix A starting on Thursday. I'm still going to give you a demo of that hardware system, but that might not be till next week. I don't know.
So, but there's an actual quiz.
There's an actual last quiz on this Thursday.